Hi guys. So we're going to keep looking at graphs of functions. We've talked about what a function is. We've looked at a couple. Now we want to look at the graph of a function and see what information we can glean from it. Really, I want to figure out as much as we can as possible. So some of this is going to be an appeal to your intuition, and some might be some vocabulary, right, that we need to formalize. You'll see a lot of times in mathematics, if there's something intuitive, um, the trick is to take that intuition and give it rigorous, sound meaning, assigning definition really to what we know to be intuitively true. So let's head over to our graph and see what we can do. All right, so graphs can tell us a lot. As I've mentioned here, we have things such as, certain behavior. What does it look like at different pieces of its domain? We can find a rate at which its values are changing over an interval. We want to get as much information as we can and then formalize. So let's take a look at a specific graph, say this one here. Now, the two most basic questions are really domain and range. That's the first place we want to start. And so let's start with the domain. And I'm going to write my domain and my ranges here in interval notation. And so when you think of domain, you really want to think left to right. So if I'm looking left to right, my leftmost value is here at -3. And notice that this point here is open, which means -3 isn't actually in the domain. Okay? And then we're going to move to the right and see what happens. Okay, I get to 0. Now, there is a vertical gap, but there's not a horizontal gap, right? As I keep moving to the right from 0, there's a vertical jump up to this piece, but there's no jump horizontally. Also, you might notice that this piece up here, right, is open at 2, but closed at 1. So in terms of our domain, there's continuity, okay? So from -3, and then as I keep moving, right, I still have 2, even though it's undefined up here at 2, it is defined down here at 2, and then all the way to 4. And again, 4 is open. And so open interval, -3, 4, okay? Think of it really as, I said I was going to do interval, but if you wanted set notation, it'd be the set of all real numbers x such that -3 is less than x is less than 4, okay? Now what about the range? So domain, we're thinking left and right. Domain range, that's the output, which is represented by the y-coordinate. So we're thinking up and down. So let's find the lowest value. Okay, the lowest value here, again, is that point. It's at -1. But now you might say, oh, -1, it's open there, so it doesn't actually achieve the value -1. Oh, but be careful, it does over here. And so we have the value -1, including -1. So closed. And then let's move up. So as we move up from our minimum, you might notice there's a gap here, but those values are still attained over here on this portion, right? So these y values get hit. This y value gets hit all the way up to 4. Does the function ever take on the value 4? No, it doesn't, right? This is open up here. It's not closed anywhere else. So open interval at 4. If you wanted to write that in set notation, you might say the set of all y's such that -1 is less than or equal to y is less than 4. Okay? All right. Well, what else could we say? I mean, what is some other interesting information here that you might be concerned with? Well, let's see. Increasing, right? Where is the function increasing? Well, in other words, where is the function, as you move left to right, where is it also correspondingly going up? Well, here's our first spot, right? Looks like it's increasing on -3 to -2. It looks like it's increasing, so union, from -1 right here to 0, and then from 0 up to 4. Okay, notice these are open, right? At 0, well, let's look at -2 first, right? At -2, you're at the top. You've stopped increasing, but you haven't yet gone down. So that's why it's open. Decreasing. Well, -2 to -1. And then 2 to 4. Okay. Oh, I'm sorry. I put 0 to 4 up here, but that's not right. 0 to 2, right? We're on the x-axis. Sorry, guys. So increasing on -3, -2, -1, 0, and 0, 2. It's looking at the range. All right. Well, what else? What are some other interesting points? If you were walking this thing, what would be some places that you'd enjoy being? Well, how about up here? That's called a local or relative maximum. And it's called local because it's the highest point in its vicinity. It's not the highest point overall, okay? So local maximum at -2, 1. How about a local minimum? Well, looks like there's a local minimum at -1, -1, right? A low point. Okay. So, and there's some other wonderful things we could notice. You know, it looks like this is it's concave down here. It's concave up here. Okay, there's changes in concavity. When you take calculus, you're going to have analytic tools to determine all of these features, including where the thing opens up or down. It's really powerful. For now, I think these are a good place to start, okay? So let's give some meaning to these, some rigorous language. A function is said to be increasing over an interval I if f of x1 is less than f of x2 for all x1 less than x2. And similarly decreasing, f of x1 is greater than f of x2 for all x1 less than x2. Well, let's make sense of that, okay? Increasing, what does that mean? I agree that if I drew a picture, you could tell me if it's increasing or decreasing, but how do we give rigorous language to it? Well, we're saying that f of x1 is less than f of x2 for all x1 less than x2. Let's think about what that means. Let's just call this random point on the x-axis x1. Now, we need a second point that's larger than x1, right? We're moving to the right. So maybe that's x2. And so f of x1, I don't know, maybe that's the value f of x1. And then maybe this is the value f of x2. Notice that f of x1 is lower than f of x2. And so we have an increase. But notice what it says here, for all. What that means is I can move this x2 ever closer and closer to x1. And as I do that, I still have a larger function value when my x coordinate is on the right. So in other words, as I move right, my function also moves up. As we move right, the function moves up, okay? Now I'm gonna let you unpack the definition of decreasing. I think it would be worth pausing and kind of giving some thought to that. What will this graph look like? And what would this statement be, okay? But play around with it so that you also have a similar experience as we talked about with increasing, okay? Now, local maximum, local minimum, those are also known as local extrema. And so a local maximum says that, or we have a local maximum at a value c, x equals c, if f of c is larger than f of x for all x in some open interval containing c. Local minimum, f of c is less than f of x for all x in some open interval containing c. What? Well, as your mathematical sophistication grows, you should be able to, and I'm not saying you should be able to right now, but as it grows, you should be able to read a mathematical statement and understand it in plain terms. When I read this first definition of local maximum, that tells me that the point is the highest point around. Maybe not overall, but at least in its neighborhood, in its vicinity. That point is the highest. Similarly, the second definition tells me that in the vicinity of x equals c, f of c is the lowest point. It's a low point in its neighborhood, okay? Believe it or not, neighborhood is even a technical mathematical term that you learn if you ever take an analysis course. Again, appealing to your intuition. If I say neighborhood, you're thinking everything around it, right? And so that's why this open interval is so important, because we're thinking everything around it. If I have an open interval, let's say A to B, if C is somewhere in here, then for C to be the high point, it has to be the high point all around. There has to be points lower than it on the left, and there have to be points lower than it on the right. In other words, you could climb up to the top from either side of the hill, okay? That's why you need an open interval. You need to be a local max or minimum, you need points to the left and the right that you can either be lower than or larger than. If I'm talking about a local minimum, if this is a local minimum, then I need points that's lower than, or points higher on the left. I also need points higher on the right. That only happens if you have an open interval, okay? So can an endpoint be a local max or min? In other words, could I have this situation? Would I call this point here a local min? No, it's not a local min or minimum, because you need points. You need points on both sides. Okay? You need points on both sides. You have to be able to approach it from both directions. Okay? All right. So my hope here is that as you've gone through this lecture, I've appealed to your intuition. Again, I could have given you a graph to begin with and said, tell me where the maximums and minimums are, where it's increasing or decreasing, and you could have observed that very simply just by looking. So we've gone a step further here and taken our intuition and applied some language to it, okay? I realize that there's some theory involved here, so spend some time thinking about it. Again, really wrap your head around why we need an open interval around a maximum or a minimum. These are going to become increasingly important as you transition into calculus, okay? We're looking at behavior over an interval, okay? And so as you move forward, you should be able to take a graph, identify domain and range. You should be able to look at the graph and say where it's increasing, where it's decreasing, and where any local extrema, meaning maxes or mins, are. All right, with that, I will leave you and wish you well in your studies.